In this segment, we will compute an example of evaluating instantaneous rate of change by definition. For our example, we will use the exponential function from the previous segments. Just to summarize, here's the function capital X sub u that gives the amount of unmetabolized drug that leaves the body as a function of time. It is an exponential function, and we will compute instantaneous rate of change for that function using the definition. We will use the moment of time t equals 12 to compute their instantaneous rate of change. That is, we will be evaluating the following limit. Limit as h goes to 0 of the fraction. In the numerator, we have value of the function evaluated at 12 plus h, and we subtract value of the function evaluated at 12. In the denominator, we have h. By computing this limit, we will evaluate instantaneous rate of change at t equals 12 of that function. So what's going to be happening next, we will work out through this limit, and that limit has a couple of difficult moments. First of all, we'll have to substitute the function in, which may be a little bit challenging because it is tedious. It's not hard, but it is tedious. And then once we substitute it, we'll have to simplify. So there will be a couple of steps dedicated just to that. Once we simplify the expression, we will have to deal with an exponential, and we will need to use a result that we didn't discuss before, probably, most likely. So we'll just use that result, and it takes care of a lot of stuff. And then we will work out the limit. So let's get started. So the first step is to carefully substitute the definition of the function x of u, and I am preparing myself for a very long expression, so I wrote this ginormous denominator line, the fraction line, right? So in the first place, I need to take value of the function at 12 plus h, so here we go, 60.0 multiplied by parenthesis 1 minus exponential minus 0.069, and here, instead of the variable t, I need to substitute 12 plus h. So here comes 12 plus h. Now I have 3 parentheses closing, lots of parentheses, but we just carefully implemented that term. So now we have to implement the second term. So I'll put a minus here, and I put 60.0 multiplied by parenthesis 1 minus exponential function evaluated at negative 0.069, and instead of t, I will put value of 12. So it's at 0.069 multiplied by 12. And as you can see, I did not have long enough fraction line, so I will extend it a little bit. So now what we would like to do, we would like to simplify this expression just a bit. So I'd like to start from noticing that I have some common like terms, like this 60 is a like term between these two. So I should be able to factor it out. Here we go. So let me just copy limit as h goes to 0 over here. 60.0 is a common factor. Inside, now let me put like big brackets here. Inside I'll have 1 minus the exponential of negative 0.069 times 12 plus h. That's the first term. And then there will be minus 1 minus exponential minus 0.069 times 12. Okay, very well. So that's the numerator, and the denominator is still h. Now notice that that factor of 60 can be pulled outside of the limit. We have certain facts about limits established in the previous section, so we can take that 60 and bring it outside of the limit. So here it comes. So it's going to be 60 times 0 times limit as h goes to 0. Now, what's going to happen, I'm going to continue. Okay, so I don't like how I wrote it, so let me try to be maybe a little bit more mindful of the space. So I would still have division by h here in the denominator, but in the numerator, I will make a few simplifications. So first of all, let us take a look at that value of 1. That value of 1 will cancel with this value of 1 because of that minus. Because of that minus, this 1 will cancel that 1. So here we go. The resulting expression is minus exponential of minus 0.069 multiplied by 12 plus h. And here, this minus combined with that minus results in a plus. Let me highlight it one more time. So let's take a look at that minus and that minus combined together gives a plus. So let me continue. It's going to be the exponential of minus 0.69 times 12. So, and that's already a simple expression, right? So we got rid of some brackets, but we can simplify more. And to simplify more, we need to remember the property of exponentials. Now, I use this exp function because that's something that is easy to do in computer programming, but we also know that function as e raised to something. So in particular, if you have exponential of x plus y, which is the same as to say e raised to x plus y, we do know that e raised to x plus y can be broken down as e raised to x multiplied by e raised to y. Now, if you would like to use exponentials, then you'll say exponential x times exponential of y. So now that is the side comment that I will need to go to the next step, because what's going to happen, we will split this exponential into product of 2. So let's take a look. What is it inside the exponential? We have 0.069 multiplied by 12 plus h. That is, of course, 0.069 times 12, that's the first number, minus 0.069 times h. All right, so my h didn't come up very nice. Let me rewrite it again. Here's my h. So these are two numbers. Well, this would be number A, and that would be number B. Well, maybe let me use x and y here, because I already start using x and y here down below. So that would be number x, and that would be number y, and I can use the formula that I highlighted over here. So exponential of negative 0.069 times the quantity of 12 plus h can be written as exponential of that, and that can be broken as the product of two exponentials. The first exponential will have negative 0.069 times 12, and the second exponential will have the rest. It's going to be negative 0.0. Okay, I don't have enough room here, so let me try again. Let me try to rewrite it. So it's going to be exponential of negative 0.069 times 12 times exponential of negative 0.069 times h. So I'm intentionally using this very complicated numbers to highlight that as a professionals, you will have to deal with numbers that don't look nice. And the success of your action depends on whether you prepare to handle these numbers and, facing some tedious work or not. So since we expect that a lot of important stuff will be done when we, go to our professions, and we expect that there will be a lot of tiny details to which we need to pay attention to, practicing with these numbers is very important because among other things, it teaches us to pay attention to small detail and go slow and try to keep every step correct. So anyway, long story short, with this calculation on the side, we can make another change to our expression. Okay, maybe I went ahead of myself a little bit again. So here, the first term will be broken into two. First exponential, 0.069 times 12, multiplied by the second exponential, negative 0.069 times h. Now, and I still have a minus in front of the whole thing, so that's okay. And here we have another exponential, which I simply copy. There's nothing that I do to that exponential. And then I have a denominator h. So to finish with this page, let us notice that I have another common factor right now, that exponential over here. So that's the same factor, and we can factor it out of the fraction and factor it out of the limit, and we will write the following. So it is equal to 60.0 multiplied by exponential minus exponential, inside exponential, negative 0.069 times 12 multiplied by the limit. Okay, you know what? So I have a feeling that I don't have enough room here to write down the result, so I will move it down here, multiplied by the limit as h goes to 0 of the following fraction. The denominator is h. The first term is negative exponential of minus 0.069 times h plus 1. So a little cramped here, so please feel free to go over the steps later and check my arithmetic. But I will move to the next slide. So what we just did, we substituted the function and simplified. We didn't do any calculus just yet, but it is coming. Well, maybe we did do some calculus. We used the limit laws to move the common factor outside of the limit. So here we go. There's some calculus here. So now all we have to do is to evaluate that limit, which looks significantly simpler, and we will be done. So that we will accomplish on the next page. So here's the limit that we just saw, but it's neatly typed here. And we notice that there is a portion that is a constant. You can evaluate it by, using calculator or something, and we do not have to do anything. So that one is already good. The difficult part is to handle this limit. So we still need to evaluate that limit. Now, the important part is that this is an exponential limit, and it is not typical for us to discuss that limit in a regular calculus course. To help us, there are many ways to approach that limit. There are some hard ways that are suitable for math majors on their real analysis course, and there are ways that you can do, but maybe not right now, but a little bit later in the course, once we learn the tools that will make it easier to evaluate this limit. So in this case, what we're going to do in between. We will use a result that is true for exponential functions, that limit is true for the exponential function, and we will try to apply it here, and that limit will do the heavy lifting. It will alleviate all of the hard work. It'll make it easy. So, but we will need to do one additional technical trick, which is useful in what you're going to be doing in this course. So let's take a look at the limit here, that exponential limit. If you are curious enough to figure out the proof of that limit, or you are accidentally a math major, and you would like to know how to do it, or maybe you're not a math major, but you really want to know how to do it, here's a nice link that gives a possible solution that is pretty involved. So if you can get through it, you should be very, very proud of yourself. So anyway, we're not going to do it for the sake of this presentation. We will just use this result. So let me take that limit and copy it over here. And I would like to apply the result in the box to evaluate this limit. Upon comparison, we see that there are things that are similar and things that are not similar. So for example, if I put a minus outside of the parenthesis, then that minus plus will become a minus, and I will have a very similar form. Exponential of something, minus 1 divided by h. So you can match. That's a similar structure. Moreover, I have similar behavior. That variable that sits here in denominator is going to 0. And watch out, this also is going to 0. So that's the same looking variable, and it's the same type of behavior. Now, that's another similarity. Now, however, if you look inside the exponential, here you will notice that in the exponential at hand, we have negative 0.069 times h. And the exponential that is in the limit here, we just have the variable t. That's not the same. So therefore, we cannot apply that limit directly. We need to do one additional step, one additional trick. And that additional trick comes as follows. We will just go ahead and pick the thing that we don't like the most in that expression that we need to work with. And I think that you all will agree with me that what we don't like the most here in this example is that term, that negative 0.069 times h. That's the thing that we don't like. Okay, so we picked something that we really don't like, and let's work with it. So what we're going to do, we're going to define a variable t that is equal to 0.069 times h, right? The moment we've done that, let me put the limit here, let me put the fraction here. Let me start work on this. So I have this minus up front, and I have this exponential, but instead of negative 0.069, I introduced that t over here, so I'll just put t over here, right? And I'll put negative 1. So look, I accomplished something interesting because now my numerator looks exactly like the numerator in that expression, right? So, however, there's a problem. Instead of, here in denominator, I have h. And I need to keep that h over here, but it doesn't go away. But the good thing is that I can solve for h from that definition. So if t is equal to negative 0.69 times h, then h is equal t divided by negative 0.069, right? So instead of h, I can put t divided by negative 0.069. All right, very good. So last step is also very important. It comes from the following observation. If h goes to 0, what's going to happen to the variable t that we just introduced? Well, let's take a look. If h goes to 0, it will have a small number multiplied by negative 0.069. And when we multiply a small number by negative 0.069, we will get a small number. So if h goes to 0, then t goes to 0. and vice versa. If t goes to 0, then h goes to 0. You can observe this fact. We can observe these two facts from the way we introduce t. So if we define t like that, then when h goes to 0, t goes to 0, and vice versa. When t goes to 0, then h goes to 0. So what that means is that the limit h goes to 0 can be replaced with the limit as t goes to 0 and backwards with our substitutions. So as a result, we now accomplished a different limit. And let's take a quick look. So that fraction can be simplified. That negative 0.69 can be brought up front. And the minus over here also can be brought up front, and they will cancel. So the resulting answer is 0.069 times limit as t goes to 0 of exponential t minus 1 divided by t. And that is precisely the limit in the box, and we know that limit is equal to 1, so the answer is 0.069. So let's just put everything together. We're almost done. So to summarize, we started with the function capital X sub u, and we wanted to look at the instantaneous rate of change of this function at t equals 12. So we applied the definition of the instantaneous rate of change right here, and we simplified that. We substituted the function and do some simplification until we arrive at the limit over here. And in the previous slide, we worked out this limit to conclude that this limit is equal, this entire limit is equal to 0.069. So here we go. That is the final answer. And if we plug that into calculator, this is what we're going to get. Now notice that only about 15 digits of this answer is reliable, the rest is not. So I would like to pause here. We have successfully computed instantaneous rate of change. And in the next segment, we will consider a couple more examples of computing rates of change.